Thanks everybody for coming to this session, the last hour of the last day. My name is Morgan Oslake. I'm a program manager on the Azure data team, Azure SQL Database team, and I'm happy that you're here to join in the discussion on something that we just GA'd this last Monday called Azure SQL DB Serverless. So in terms of the agenda, we want to get through what is serverless, to some extent what motivates serverless in the first place in the database world, when to use serverless, but just as importantly, when not to use serverless. It's not a panacea. And then how to use it, and as part of how to use it, how does it actually work under the hood, in as much as the inner workings impact the actual price and performance experience for you, the customer. So to motivate this, there are a lot of different kinds of challenges in optimizing price and performance, especially for database workloads. I'd like to sort of illustrate some of those challenges by way of example first. Scenario that involves an IoT application. Imagine this app is managing sensor weather data from weather stations that are geo-distributed across some large region. Suppose maybe the weather stations are reporting, maybe it's an agricultural application, and the weather stations are reporting rainfall. And so, on relatively dry days, and suppose also the application is smart enough not to transmit rainfall data if there isn't a change. So on relatively dry days, there isn't much being transmitted to the database, but then, a storm can blow through. It can be a big storm, a small storm. If it's a big storm, it may be impacting lots of the, sort of the rainfall collection tipping buckets are falling over in various parts of the region and sending a lot of information to the database. Maybe it's a localized rain shower, and so there's just a slight increase in the number of events reaching the database. But most of the time, it's relatively low usage profile. And so one thing that unites, one sort of common theme in this scenario is that is the workload pattern, the usage pattern on the database is not just unpredictable in terms of the time at which data actually arrives to the database, but it's also unpredictable in terms of the amplitude, the amount of data. When that storm blows through, there's going to be a huge amount of data. And then, it can become further complicated if there are web users, maybe farmers that want to are eager to see what the rainfall totals are. And so maybe this same database has a web front end, and when the storm blows through, people are more likely to log on and check the rainfall amounts. So that just sort of further aggravates the problem and adds more uncertainty to the usage profile for the database. So this presents a lot of DevOps challenges, obviously, especially with respect to how to size the compute for the workload. You can decide to over-provision resources for the database and to ensure that the performance is nice and happy and healthy. But given the pattern of usage for this database, there's going to be a lot of time where there's just sort of wasted cycles. So the alternative would be, well, you could somewhat under-provision resources, but risk performance penalties. So it's really hard to get the right amount of spend for the right amount of performance. If it's an app in the cloud, then you can take advantage of, sort of an air quotes cloud elasticity and rescale the compute of the database, and even think about writing your own automation on top that does scaling for you. But that becomes tricky when you really start to get into the details. You have to think about, well, do I rescale on a schedule? Well, probably not for this application because weather doesn't run on a schedule, certainly rain doesn't. So what's left is perhaps triggering a scaling operation as a function of crossing some kind of usage threshold. But then when you get into those details, first of all, what are the right metrics to consider? What's the right threshold? And then once that's been decided, what's the latency of the rescaling operation? You know, if it takes a long time to rescale, then that storm may have blown through by the time you finally upsized your compute. And now the automation is trying to downsize, and then another storm blows through, so it's never really able to keep up. It's kind of chasing its tail in terms of where that sizing is. So it becomes challenging. So let's think about how this kind of application might fit into the set of choices that are offered within SQL DB. Before I go into this, so these next two slides are a bit of a preamble to serverless to sort of set some context. How many people here, just a quick show of hands, have ever deployed a database in the cloud? Start there. Okay, awesome. It's completely interesting to see how the show of hands changes each year. How many people have ever deployed a database in Azure SQL Database? Okay, good, that's great. So these aren't new concepts. I'll go over them rather quickly. There's essentially 3 deployment model choices. It's sort of the first level of decision making if you want to go into SQL Database. Managed instance, as I'm sure many of you are aware, is ideally suited for lift and shift scenarios. It's got very high application surface compatibility. It's designed to reduce friction in migrations from on-premise into the cloud. Designed to minimize the extent to which any kind of application rewrites have to occur. And there are elastic pools. Elastic pools are a resource sharing model concept. They work really well for customers with a lot of databases that can pool those databases together into the same set of compute that gets shared across all those databases, and it lowers the cost quite substantially. It works, you know, a typical kind of customer for this would be a SaaS ISV. They could have tens, hundreds, thousands, tens of thousands. We even have some customers that have hundreds of thousands of databases for the same application running in elastic pools. And then finally, the third choice is single database. And this is sort of think of single database as the simplest deployment option, but simple doesn't mean bad. It just means it's simple. Everything's fully managed. Good performance predictability in terms of resource allocations, especially well suited for cloud-borne applications. So maybe this IoT application that we talked about, this weather monitoring app, being written for the first time, might be a good candidate for single database. And in fact, serverless is currently offered in the single database deployment model, not in elastic pools or managed instance, at least not yet. Then the next sort of set of choices relate to, once you pick the deployment model, what service tier makes sense and what compute tier makes sense. One way to think about service tiers, the way I at least think about it, is it essentially defines the storage architecture for your database. So things like the max storage size, and the general purpose tier, you can go up to 4 terabytes. Business critical goes up to 8 terabytes. Hyperscale, I'm sure many have heard by now, it goes sort of limitless scale up to 100 terabytes and more. I/O is one of the one of the most important differentiators between these service tiers. So if you think about sort of IOPS on the business critical tier, it delivers more or less 10 times more IOPS per unit of compute. So if you just say normalized per core, 10 times more I/O than, say, the general purpose tier. Latencies are also fast in business critical, 1 to 2 milliseconds, sometimes microseconds, sometimes just below that. Whereas in general purpose, latencies are, several milliseconds more. Still usually under 10 milliseconds. It's not bad, but not quite as good as business critical. And then hyperscale, in terms of I/O performance, sits somewhere in the middle at super high level because it has a storage hierarchy that is closer to the compute than general purpose, but a little bit further away than business critical. But it tends to skew in terms of its I/O qualities and performance closer to the business critical tier. Business continuity is obviously a super important dimension that really is more anchored in the service tier. So by business continuity, I mean things like the number of replicas for HA, The business critical tier has 4 replicas, 1 primary and 3 secondaries. That also facilitates read scale out, so you can take a business critical database and for no additional cost, you can turn one of those 3 secondaries into a read-only replica. On the other end of the spectrum, general purpose has a single replica, and then hyperscale has a configurable number. Other sort of business continuity dimensions that are important that are defined by the service tier you pick would be things like restore operations. So the tech behind backups in hyperscale uses snapshots. That makes restores really fast. I don't know, I think there was a hyperscale session just before that. You can restore any size database in constant time, even like tens of terabytes you can restore in under 30 minutes. Whereas the restore times, because these storage architectures are much different in general purpose and business critical, are more proportional to the size of data. It could take several hours for a restore. And then finally, another important distinction are things like zone redundancy and availability zones. Those are available in business critical, increase your number of 9s. They're not, I'll say, yet available in these other 2 service tiers. And then this sort of third decision, once you've gotten through deployment model and service tier, I should say that serverless is supported in the general purpose tier right now. And then finally, there's the decision about the compute tier. And there's no specific ordering here in the decision tree. This is just tends to be the way I think about it. There's provisioned compute and there's serverless compute. At a super high level, the compute tier defines the amount of CPU and memory for the database. Some more details like the hardware generation that the database is running on. We've had mostly Gen 5 hardware for a long time, which is sort of this well-balanced hardware, well-balanced between compute and memory. And we just announced also this last Monday the preview of 2 new hardware series. One called M series, which is memory optimized. It increases the memory to vCore ratio. It's like almost 30-to-1, whereas in Gen 5, which is the one that's been out there for years, the ratio is more like 5 or 6-to-1. So, and the total amount of memory goes at the top end on Gen 5 from like a half a terabyte up to 4 terabytes. 128 cores instead of 80. So the M series is a big beefy thing. It's pretty expensive. And then FSV2 is compute optimized, so super fast clock speeds, which would be useful if you have applications that are sort of more single-threaded in terms of how they don't sort of lend themselves to being parallel. We'll talk more about serverless. This lower right-hand square is what we're going to dive into in this session. At a high level, serverless is this compute tier that auto-scales the compute. And by compute, when I say compute, I tend to mean not just CPUs, but memory and I/O to some extent. It also has this other mode that it automatically pauses and resumes database. And we're going to drill down into each of these characteristics. And then on the billing side, it just charges for the amount of compute that your database uses rather than the amount of compute that your database is provisioned, which is a huge distinction between provisioned compute and serverless. And it charges on a per second basis, whereas provisioned, the smallest granularity for billing is an hour. So if you're, if you're in provisioned compute and you're in 1 core and you just need 4 cores very briefly, and you upsize to 4 cores, and you just needed them for 5 minutes, you're still going to pay for 4 cores over at least an hour. Whereas in serverless, if you needed 4 cores for just 1 second, then you're just going to pay for that 1 second of usage of 4 cores. In terms of sort of the manageability PaaS benefits of SQLDB, they're all the same for serverless. There's no distinctions. It's not like serverless is, managed instance is a little bit like this. It's kind of it's under the SQLDB umbrella, but there's some friction in, say, moving between managed instance and single database and elastic pools. It's not like serverless is yet this new thing that just from a marketing perspective is under the SQLDB umbrella. It's fully integrated into that product for single databases and has all of the Manageability benefits, automatic service updates, automatic backups, built-in intelligence like auto-tuning, you get index recommendations to speed your database up, security optimizations, all that's just there. And I should have said at the outset, anybody has questions, just feel free to raise your hand and interrupt me. We don't have to certainly wait until the end for that. Okay, so let's start to ease into, like I said at the beginning, it's serverless, it's not appropriate for every kind of workload. And qualitatively, the kinds of things to think about in terms of whether or not serverless is a good fit relate to the usage pattern of the database. So if the workload pattern is intermittent, it's unpredictable, it's got sort of relatively long periods of low or idle usage, but points in time where it needs to burst to some number of cores or some amount of memory, then that's the first good sign. One way to sort of quantify that is in terms of its average utilization. If the average utilization is below a certain threshold, over some period of time that essentially captures your business cycle in terms of its usage patterns, if it's below a certain threshold, we'll get into details later because it relates to specific price points, then serverless that's another good sign. On the other hand, if usage is, on average, is quite high, then chances are provision compute's probably the better place to be. If you're working, say, with one of your own customers and they happen to be struggling with rescaling databases, say in the cloud, that's almost an automatic indication that serverless is probably a good fit. I mean, this just does that for them. And with much fewer performance penalties that we'll get into a little bit later. Then finally, new databases. You could almost sort of, when it comes to new databases, throw away everything I just said and think about a situation where you just have no idea before this app goes online what the sizing requirements are. You could consider putting it into serverless, rely on the fact that it's going to auto-scale resources for you so that you'll be solving the performance problem, and then over time determine whether or not your price optimization goals are achieved as well. And if they're not, then you can easily move that database back out of serverless and into provision compute. So it would just give you an opportunity to sort of have it somewhere safe in terms of performance, be able to observe its utilization history, and then that would be able to guide better what amount of compute in the provision compute tier makes sense. In terms of sort of anti-patterns for serverless, what doesn't work well, it's almost just the opposite of everything we just talked about. There are, besides sort of the degree of usage, the average utilization, there are two performance penalties that impact serverless databases. They both relate to how resources get reclaimed, and we'll get to that a little bit later in detail. But on the provision compute side, by definition, those resources are always there. So I like to think of provision compute as having really high quality performance dial tone. It's just always there. The serverless, there may be some warm up involved. And so if your application can't tolerate that warm up penalty, then it may not make sense. And then finally, sort of already mentioned, if you've got a lot of databases, elastic pools tend to be the best place to be. All right. In terms of, so people often ask, well, what kind of applications make sense? Say outside of that IoT app example I just gave. The sky's the limit. Really, it's up to your imagination. It's the usage pattern that matters. But dev and test workloads are one obvious choice. Line of business apps also work quite well. We have a customer, for example, that's running their payroll and accounting system, their payroll and reporting system on serverless. Another customer that's running expense reporting on serverless. So that customer has sort of relatively high usage, but bursty usage during the day when their employees are filing expense reports. They do some batch jobs at night, and the frequency of those batch jobs tends to increase as they near the end of the quarter or semester or the end of the year. But all of the usage pattern is still fairly unpredictable. Yeah.
So when I'm trying to think of this and how it compares to Azure SQL Database and managed instances,
Huh?
if in Azure SQL Database you have an option where you can say, let it auto sleep whenever nothing's happening, is that effectively what this is, or is that a bad analogy? Or
No, that's it. So the question is, within the context of Azure SQL DB, is this essentially an offer that sort of auto sleeps when the database isn't being used? I would say that's sort of half of it. The other half of it, when it's not asleep, when it's online, how it's rescaling resources to match the demand from your workload. Or there's this good fit between usage and allocation of resources. Sure. Another example, content sort of management systems. There's a lot of good use cases here. We have another customer that has mapping, basically a map of Earth that they provide to third parties who do their own pulls of different parts of Earth at different points in time. I mean, this mapping database has, cities, it has roads, it has distances between roads, all the things you might expect in a typical mapping database. And the customers of that database pull different parts of Earth at different points in time, and there's no control, there's no schedule when those third-party customers do that. It's very unpredictable. And then the map itself, the mapping system itself, occasionally has to be updated. So it has feeds, and of course, this customer controls when they update their own database, but when they do, they're still always uncertain in terms of what the actual compute impact is going to be and how big that compute, how many compute resources they're actually going to have to deploy. So they found serverless quite useful as well. In terms, okay, so sort of, this is sort of starting what is serverless. Two things again, it auto-scales and it pauses and resumes. So on the auto-scaling side, the customer, you can configure a minimum amount of compute that's defined by min vCore setting and a maximum amount of compute that's defined by a max vCore setting. And these min and max vCores are proxies also for min and maxes of memory and I/O. So you dial in that range of compute that you want to provide, allow your database to have access to, and the service will take care of scaling the resources within that compute band. And so for example, if I've set the min vCore to 1 and the max vCore to 8, if at 1 second in time I'm using 1.5 cores, and some amount of memory, then I'm billed for 1.5 cores. If at the very next second in time, the database requires 8 cores of compute, then the bill is for 8 cores of compute at that very next second. And those costs just add up over time. If the usage is ever below the minimum number of vCores and the minimum amount of memory, those compute minimums are still charged. So you can see that. Let me see if I can zoom in a little bit. In this graph here, these green lines up, so this gold line is usage over time, and these green lines represent the amount that's actually billed. And think of a slice of one of those green lines as just 1 second. So when the usage is, say, between 9 o'clock and 5 o'clock in the day, when it's above that min vCore setting, it's really just being billed for auto-scaling and being billed for the amount of compute that's being used per second. Outside of that time, say after 5 o'clock, when the usage starts to come below that minimum vCore amount, the minimum number of vCores is still billed. There's a minimum amount of compute that's kind of online so that it can respond, the database can respond quickly if activity returns. But if the database is idle for a configurable period of time, which is this parameter called the auto pause delay, then the service will automatically spin the database down. It automatically pauses. And then, yeah, question?
When it scales up, like auto scales up or auto scales down above that threshold, do you have to worry about transient errors?
Not in the auto-scaling part of the workflow. When you're sort of spinning up from being paused, you have to sort of Right, okay, that's a great question. We'll go into it a little bit later, but the question was, when it's quickly changing its scale requirements, say from 1 core to 8 cores, as the autoscaling is transitioning between those levels, is there any kind of transient error impact to the database? And the answer is usually not. And I'll try to make that a little bit more precise. There's usually no impact to the database at all. The worst impact to the database would be drop connections, but that happens very rarely. So then if going back to the example, if the database has been idle, say, for an hour, and it automatically pauses, then at that point in time, the instance is actually shut down, it's terminated, and all that's left are remnants of that database in terms of its storage footprint, and it's the storage that's, it's just the storage that's left to be billed. So the compute bill goes to 0. So the price savings can be rather significant when that occurs. Onboarding is really simple. It's just like creating a new database in provision compute. It's really no different. I just threw up this PowerShell example and highlighted in yellow the new parameters that need to be used to in PowerShell create a new serverless database. But it's still, new Azure SQL Database. You specify that the compute model is serverless, and then configure these 3 knobs, the min-max vcores and the auto pause delay. Existing databases, similar story. If you want to move a provision compute database either from the D2 model or vCore model into serverless, it's 1 set command in PowerShell, 1 mouse click or so in the portal experience. There is, and there's no application rewrite at all, except if you plan to use auto pause and resume, it's absolutely essential that the application have retry logic built in. And that's because the first connection attempt or 2 will fail on a pause database. So it must have retry logic. Yeah, question in the back.
So the autoscale, is that only CPU or also memory?
Memory and CPU. The question is, what is autoscale scaling? It's scaling CPU and memory both.
Usually SQL holds memory or uses memory for a long extended time, so how does that affect the autoscale?
Yeah, it's a great question. Question is, SQL tends to hold on to memory, so what happens when the workload is relatively idle? What do we do with that memory? we'll have a section on that. We'll get to that. It's a great question. Yep, question.
So when you define inactivity as it relates to the pause, that is absolutely like 0 connections, you're saying?
Yeah.
Like if I left the management studio open or I'm monitoring from a third-party app, those are all going to keep it up above the threshold?
Yep, so 0 activity means, yes, 0 connections to the database, and CPU is exactly 0. Yes. Question.
The auto pause delay, is that minutes? The unit?
The unit, in API it's in minutes, but the lowest value right now that's supported is an hour. We're looking into making that the smallest value even smaller than that.
Is there a setting you can supply to the auto pause delay where it never sleeps, essentially to avoid having to have that retry logic?
Yeah, that's a great question. So is there a way to essentially disable pausing and just take advantage of the autoscaling part of serverless? And the answer is yes. Yeah. There's a checkbox in the portal where you pass in -1 as a parameter to that. Yeah. Good question?
So is it just as simple to go back to a server-backed model?
Yeah. The question is it just as simple to go, say, get out of serverless? It's not like the Hotel California. You can check in and you can check out. Yep. In fact, this is a good point to jump into the first demo here. So let's do that. It's just the onboarding demo. It's kind of what I've just said, but I'll just show it to you. So suppose, let's see. Here we go. So I've got this logical server. It's called LS3. It's got about, 10 or 11 databases. You can see over here on the right-hand column, most of these are serverless databases with varying numbers of max vcores configured. And then I've got a couple of databases down here that are provision compute. One, S4 in the D2 model, Can folks see that? Okay. I've got an S4 here and a provision compute for vCore database as well. So let's suppose my intention is to move, this database, this provision compute database, into serverless. Okay, so just click on it. And you come to the overview blade for this database. It's not very interesting. It's actually doing nothing right now, but it is online. And to move it over, I just go to configure, which opens up a new blade where I essentially can parameterize sort of high-level performance settings. I can also switch service tiers that we talked about. So right now, this is in the general purpose tier. I can move it over to hyperscaler business critical, but my goal right now is just to go into serverless. So it's simply clicking this tile. When you click the serverless tile, I've made the decision to switch my compute model from provision to serverless. It's on Gen 5, and I just have these three choices to make in terms of max vCores, min vCores, and the auto pause delay. You'll notice that, well, first of all, I was in a 4 vCore provision compute database, so I'll probably want the max vCores to be at least 4 here. Now, I can go higher, obviously. Notice as I increase the number of max vCores that the memory limits here are changing, right? So, as well as the allowed number of min vCores. So there is, the high-level statement here is there is some correlation in terms of your choice of the max number of vCores in terms of the amount of memory, what that memory range is, as well as what the minimum amount of compute is. A lot of the sort of the min memory required, one of the reasons why it increases as the core count increases is because we need to sort of start allocating more and more memory for the schedulers for each of the cores. And then if I go, I'll say all the way up to 16 cores, my min vCore is now 2. So there is a price impact here. Again, if the database isn't busy, but it's online, the bill is based on min vCores. So, if you want to be able to burst to 16 cores, there'll be a higher price to pay when it's online and not busy. And then down here, you can set the auto pause delay, or to the earlier question, you can just uncheck auto pause and it turns itself off. Yep.
Is the relationship between memory and CPU linear, or is it based on use?
The question is the relationship between CPU and memory linear in terms of how it's provisioned? It's linear at the top end. So when I change, short answer is roughly yes. When I change the number of max vCores, essentially it's a 3-to-1 ratio. So 16 times 3 is 48, and that multiplier of 3 more or less holds as you move the max vCores up and down. It's not as simple in terms of min vCores, mostly because we're just doing that in terms of, again, these threading and schedule overheads, which don't quite have the same nice linear kind of scale. But high level, that's a correct statement. Okay, and then once I'm satisfied with my settings, I just hit apply, and it takes a minute or two to move into serverless. Your data, you can have a production workload running in provisioned, and make the switch. The move into serverless in terms of impact is just like the move, just like the impact would be if you're rescaling compute within the provision compute tier. So database is fully online. Except at the very end of the rescaling motion, some connections get dropped. That's just to get the database into serverless. And like I said earlier, there are some conditions once it's in serverless that there can be impact in connections being dropped if resources are scarce. But for the most part, the rescaling is totally transparent to the customer in terms of performance. There's no drop connections most of the time. Okay. Let's see here. Let's go back. All right. So a little bit about the architecture. Partly, maybe some people are curious, but almost more importantly, it will serve as a reference point to talk about some of the more details about scaling, about auto pause and resume, and about how that impacts the customer in terms of price and performance. So at a high level, you can think of the SQL database service as a whole as having sort of 3 planes of management. There's a control plane, a data plane, and a storage plane. The control plane has several components. It has a gateway that manages connectivity. So this is where authentications occur. And it's got a management service which it handles operations, CRUD operations like creations and deletions, things like this. So you can imagine, let's do it this way. Let me bring up a little, where's my laser pointer? Right here. Let's do this. Let's suppose that I've got a database in serverless and it's paused. Let's walk through sort of on this diagram how that thing transitions from pause to online, and then talk at a high level a little bit about what happens to resource management. So first thing that happens is the client sends a request to open a connection. It hits the control plane, the gateway authenticates, and immediately the gateway transfers control to the management service, which knows that this database is paused. And so it knows it needs to find a place in the data center where there's enough compute to support spinning that database back up. So the management service finds a tenant ring. So, pick your favorite region. There's lots of tenant rings within a given region. A tenant ring is just a boundary. It's just a container of machines that run workloads, multi-tenant workloads. Order of 100 machines in a tenant ring. It's sort of like a fault domain of sorts. And some tenant rings are busier than others. So the management service says, oh, okay, tenant ring 3, that's where I'm going to put this, that's where I'm going to spin up this paused database. And so then it transfers control to this thing called the Service Fabric Load Balancer. And the Service Fabric Load Balancer, one of its jobs is within a tenant ring is to identify one of the less busy machines. So management service has sort of this macro view of the world in terms of these collections of machines, in terms of busyness, and then the service fabric is living and running inside of each of those rings and says, okay, machine 47, that's the one that I want to spin this database up on. And so then it spins it up, it launches essentially a SQL instance, and then once that SQL instance is running, one of its last steps is to attach the database files that are off in remote storage. The database files for almost all of the for all the general purpose databases, they live in premium storage. It's not like cheap storage. It's not like Blob Store or someplace like that. It's SSD storage. It's just not co-located with compute like the business critical tier, right, on the same machine. It's somewhere else, but in the same region. So once those database files get attached to that SQL instance, signals returned all the way back to the client says, okay, you're online now. So now the database is online. It can take and process queries, and as the database is processing queries, there are several services running in addition to the service fabric, like this thing called RG Manager. It stands for Resource Governor Manager. This component, there's one per machine, and it's constantly analyzing the usage of the machine and orchestrating responses if that machine gets too hot. For example, to an earlier question, what's the impact of rescaling? Most of the time, when I say most, I mean like probability put it this way, less than a fraction of a percent of the time, the database in serverless will feel the rescaling. The balance of that time, so several nines, the database won't see any kind of impact from rescaling. But what could happen is the machine could be hot, getting hot as that database is, say it's bursting from 1 core to 16 cores. If some of those cores for that serverless database, out of those 16 cores, let's say cores 1 and 2 are actually quite hot, and the balance of the cores have plenty of room to absorb more workload, but you still need those 2 cores out of the 16, then this RG manager orchestrates essentially reaffinitizing those 2, or that database from those 2 hot cores to 2 colder cores on that same machine. And that reaffinitization is totally transparent to the workload. There's no drop connections, no resets of memory. Sure, there's cache on chip that is destroyed when that database is moved to 2 other cores, but we even sort of respect NUMA nodes. So, these are big machines, they've got 2 NUMA nodes, and we have to sort of reaffinitize from one pair of cores to another. We do it on the same NUMA node. What's nice is it's super fast. It's like a microsecond. So super fast response time to resolving that kind of performance bottleneck on the same machine. Now, like I was saying before, there will be cases where all cores are hot. The machine is just overloaded, it's on fire. And if that's happening, RG Manager still detects that, but then it will ask the Service Fabric for some help. And the Service Fabric will say, okay, out of all these 100 machines, yeah, I see that machine's that you're on right now is really hot, but this other machine over here isn't, so I'm gonna move the workload there. And while it's moving the workload over to a machine that has more capacity, the database is still online, still processing workload. It may be slowing down a little bit. And then at the end of that operation, when that database is essentially reinitialized on that target machine, the connections from the machine that was hot automatically get redirected to the new machine that has the new version of the database. And it's just in that moment when those connections cut over that the experience for the customer are drop connections. But that, I should say, by the way, that's what happens all the time necessarily if you're rescaling in the provision compute tier. That just happens all the time. Yep. Sorry, say.
What happens with the buffer cache and procedure cache if that were to happen?
Yeah, so the question is what happens to the various caches in SQL if essentially under the hood there's a failover event in response to a hot machine? They're zeroed. So they'd have to be rehydrated. Yeah.
Do you guys have a alert or event or something at DMV that will let us know that happened? Telemetry that'll say that happened versus the normal?
It can be inferred from some telemetry. Okay, so I need to do a time check here, okay. One thing that's interesting is sort of the anti-correlation between CPU and memory usage. So this is a scatter plot showing memory usage and CPU usage for a lot of databases, maybe, I don't know, over 100,000. Doesn't look like it, but there's a lot of points on this chart. Showing over a week what the average memory consumption is and what the average CPU consumption is for all these databases. And you can see that these aren't like, if these were completely correlated, this scatter plot would be have a strong tendency to be clustered along this diagonal axis, right? But instead, there are cases where well, I mean, I guess this might be obvious if say you're doing a select star and you're doing table scans. Okay, there's not much CPU usage, but you're going to use a whole lot of memory. But there's other applications that maybe just require just a little bit of memory. Maybe they're doing, I don't know, mathematically intensive operations. They don't need a whole lot of memory for that, but they're using tons of compute. So this fact influenced how we actually went about designing the scaling for serverless and SQL DB. Essentially let memory and CPU scale independently of each other. So, you can have a database that just requires 6 gigs of RAM, but needs 16 cores. That's a weird ratio. I mean, just think about the memory to vCore ratio there. But the serverless offer lets the database establish that balance in terms of resources that are allocated against the actual demand of the workload. In other words, whatever the workload pattern happens to be, the database can sort of adapt. It adapts to any point in this bounding box, right? You can another way to think about this is the memory to vCore ratio is adaptive. If you take a database that is using 2 cores and needs 48 gigs of RAM, well, that's a 24-to-1 memory to vCore ratio. So and then all these points in between. So there's quite a bit of adaptiveness in terms of how resources are delivered. This isn't just good for performance, but this is good for price optimization as well, because at the end of the day, the amount that's paid is this blended measure of memory and CPU consumed. So that's how that works. Yeah.
So you would say if I have selected 4 maximum CPUs
Uh-huh.
and 1 vCore, that corresponds to maximum memory of 12 GB, isn't it? So you mean to say that even though I have put 12 GB, if my load needs 24 GB of memory, it will still go without increasing the number of cores?
The question is kind of, what are the memory limits? How do they scale in response to the workload demand? So the example was, if you have min vCore of say 1 and a max of 4, that's a compute range that you as a customer have programmed and will respect that. And for 4 vCores, that app will never be able to consume more than 12 gigs of RAM. So
you can't go above the range that you have given when you are setting.
Right. A common question is, why on earth, if this thing auto-scales, why on earth do I even need to bother setting a max vCore in the first place? What's the point of that? Partly, as we saw, it influences what the min vCore setting, which impacts the billing quantity when the database isn't being used. But also, it's a way to cap your own spend. Yeah. Maybe maybe you run a dev department and you don't want any of your devs to ever use more than a certain number of cores. You can sort of have that kind of policy in place. We talked about scale-up times. So if you compare that against provision compute, what's the difference? Well, so imagine in this example where the database needed just 6 gigs, but needed to scale up to 16 cores. In the provision compute world, 6 gigs, if I provisioned 2 cores, I would get 6 gigs, but I need 16 cores. So I actually need to provision 80 gigs in provision compute to get the 16 cores my database needs. I don't need 80 gigs in this example, I just need 6. But to get 16 cores, I've got to scale up to that amount. So that's, in a sense, wasted resource, right? So you can think of, as you scale in the provision compute tier, which you can still do, you're always sort of constrained by these boxes in terms of it's like this configuration space of aligning workload demand with resource allocation. Whereas in serverless, on this example, with one set of settings, you can explore that whole box. It's scale up. So one last time. So in the provision compute tier, the scale up time is always at least a couple of minutes. That's true in the general purpose tier and hyperscale. Business critical tier can take, it's the size of data operations, since there's actually copying of data from one machine to another. That can take hours. Memory is always reset, so there's always an internal failover. The whole memory is reset when a database is rescaled, and then connections are always dropped. And these are just things, once again, that can occur but rarely occur in serverless. Most of the time, the scaling is practically instantaneous. So let's see a demo of this. Let's go see if this, yeah. Okay. So let me just, what I'm going to do is in this demo, so the purpose of this is just to show you how fast things scale. I'm going to run a couple of really expensive queries. So these queries, I found this on Stack Overflow actually. It's, maybe you guys have seen this one before too. So it's nice. It's grabbing a bunch of system objects, dumping them into a table. The table's huge. It's then doing some aggregations and some joins. And the optimizer just can't keep up with this. So the CPU usage is going crazy. So if I come over here, I'm going to look at this DMV, the resource stats DMV. The resource stats DMV, let me run this. So this resource stats DMV, it's the most real-time way to, the nearest real-time way to measure resource consumption. It doesn't actually ever go to any on-disk location. It's basically this DMV just connected wherever, I think this is, I'm in central US, just connected to the instance in central US and pulled back the last hour's worth of resource utilization data, where the granularity of each of those data points is 15 seconds. And so what you can see here, oh, forgot to do this. That's when I ran the query. All right. No. Let me zoom in a little bit. All right. So what you can see here is that the query started roughly around 22 minutes and 11 seconds. And I was consuming almost all of my max 8 V cores, 99, virtually 100% at 22 and 31 seconds here. So that's about 20 seconds later, and that's more or less within the tolerances of the granularity of that telemetry, which is, again, collecting statistics every 15 seconds. So that was pretty fast. Now, it's one thing that it's worth pointing out. There are some other solutions out there, some serverless solutions, other solutions that build autoscaling on top of provisioned. Because they don't have this fast scaling speed, they have to sort of get ahead of things, and they may have to set sort of a lower threshold for when scaling is triggered, so that by the time the workload actually really needs more resources, those resources are provisioned, and the triggering of that rescaling motion earlier than when it needs to occur at lower usage thresholds represents essentially wasted resources too. So, there's nowhere, no point have I ever had to deal with setting thresholds for anything. The service is taking care of this for me. All right. So this goes, there were some good questions earlier about how does memory really work? So I'm sure most people in the room are aware that SQL, for good reasons, historically is really greedy when it comes to memory. And this makes perfect sense in on-prem worlds where your outlay of capital costs for machines and hardware is fixed. You buy a certain machine and that memory is just there whether or not you use it. And so, as a workload is, let's say in this example, as it's ramping up, it's allocating more and more memory, and then eventually it sort of starts to quiesce and quiet down a little bit. All of that allocated memory, it just stays persisted, and historically for good reasons, because if their query comes back a little bit later, it'll just be faster because it's already in cache. But this doesn't align very well with the serverless principle. especially one where the billing model is based not just on CPU use, but memory used. I mean, if I told you that here's the serverless thing, we are charging you for CPU and memory, and then we never reclaim memory, then what's the point? So we reclaim memory, and we'll get into a little bit more details of how that works, but do it rather gradually. We try not to be disruptive. And so the question is, what memory do we reclaim? We just reclaim caches. All the 100 caches in SQL. The big ones, of course, are buffer pool that hold the data pages, the plan cache for query optimizations, the cache for column store data. Then there's this other kind of memory. Obviously, it's important for query grants, but it's sort of convenient that query grants, in terms of their usage pattern, magically already align with the serverless paradigm, right? So query grants get allocated in preparation for running the query. Query gets run, and maybe as part of that, the SOS, it steals from the buffer pool, gives some of that memory to the grant. The query runs, grant's no longer needed, those pages get returned to the buffer pool, and so it sort of just naturally grows and shrinks anyway. So we didn't have to touch how we manage query grants. We just had to manage or touch how we manage the cache. So how does it actually work? So we have this concept of an active cache utilization. So think of all these caches as there's cache entries. I'll just call them pages, but it's not just buffer pool pages. It's all these other caches too. We added timestamps to every single one of these caches. And every several minutes, we look at we look at all of the pages that we declare as hot. And a hot page in serverless means that it was last touched in the last 30 minutes or so. And then we look at the size of that page. And for buffer pool, they're always AK pages, but if it's a planned cache entry, it could be a few K to several megs. So we basically sum up the size of all those hot pages. So that's the total sort of hot page size. And we divide that by the total size of the cache. And that ratio is this active cache utilization. It's a measure of how actively the cache is actually being utilized. And if that utilization is below a threshold, then and only then will we trigger a process to begin reclaiming memory. And we'll reclaim it gradually, sort of as a step-down function. And the way memory gets reclaimed, it's not as if we're reclaiming just the colder pages. I mean, chances are if they're colder buffer pool pages, we'll reclaim those. But the idea is to reclaim pages that are cheap to rehydrate, like buffer pool pages. An IO is pretty cheap compared to, say, if we got rid of a plan cache entry, it could be really expensive to recompile. So that's what this diagram is representing over here. These are the sort of set of hot pages. This blue bar graphs are the set of cold pages. Let's say this is a toy example. We've determined that the first round of reclamation, we just need to reclaim 3 pages. Well, okay, sure. We're reclaiming 3 pages, but not all of them are the coldest, right? They're the cheapest. And this hot page may have been in the buffer pool, but one of these colder pages or one of these pages that's colder was used much longer ago may have been a really expensive plan cache entry that would be hugely costly to recompile, so we won't touch that. And so so we'll step down in terms of, so then we'll do those evictions and wait a few more minutes, analyze the workload history, and just, rinse, lather, and repeat. If the workload returns, then the system doesn't gate at all how quickly this memory can grow again. There's no controls on that. It just can grow as fast as it can. So gradual reclamation, unconstrained growth when required based on workload demand. Does that answer some of the questions about how cache memory is managed, okay. All right. So pause and resume. We mentioned the transitioning from online to pause, 0 sessions, 0 CPU usage. I should clarify, there's all kinds of CPU usage. There's all kinds of pockets of pools of resources for your database. There's what we call the user pool, which is sort of the innermost, think of Russian dolls, it's the innermost container of resource, and that's the set of resources where your queries are actually running against. Then there are system pools, and the combination of these user pools and system pools are contained by the SQL Server instance itself. And so if the system is doing unimportant things like collecting telemetry, that doesn't interfere with the ability of the service to pause the database. It's only when queries from the actual customer workload. So you can run like a DMV, or you can see usage information in the portal experience or whatever. That's coming from system resources. That's not going to block or interfere with the ability of the database to pause itself. What happens when it pauses, we basically ensure a safe and clean shutdown. So we take tail log backups, and that's kind of the step that adds the most variability to how long it actually takes to do the pause operation. Mostly, it's sort of about a minute, but it can take up to maybe 10 minutes or so to complete that operation. Then once the tail log backups are safely collected, the database files are detached from remote storage, and then the service terminates the instance. It's gone, and then the billing for compute stops at that point, and there's just storage billing that's left over. And then when a database logs in and it can be paused for any length of time. The only thing that can interrupt a paused database that you don't control is when we do a service update. There are some service updates that don't impact the state of a database being paused, but there are other kinds of updates, sort of more heavyweight updates that require actually bringing the instance online to maybe update some system tables in the SQL Server instance or something like that, where that database will come back online. So if you ever see a database come online when you're sure you didn't do anything, that could be a reason, but it doesn't happen very often. Then, at some point, login is received, and that's the trigger, as we've talked about before, to actually spin that database back up. So let's give a demo of resuming. Oops, yeah. So here, let's do this in PowerShell. So I've got, let's see if this works. I'll just check on the status of all these databases that we saw in the portal before. Yeah, I've got 11 or 12 total databases. And so 4 of these are all online, serverless. These ones numbered 1 through 9 are serverless databases. I'll pick database 8, it's paused, and let's see what happens when I try to connect to it. So here's the script for that. Let's do that. So the main thing here is I have a loop. It's not complicated. I just have a loop. I'm just going to try over and over again to retry opening the connection to the serverless database. I'll stop, I'll give up after some number of times, and each time I try and fail, I'll wait just a couple of seconds. So let's run this and see what the experience looks like. I don't need that. What's this? Okay. So it's already authenticated, happens really fast. And like we talked about before, management services back there, it's found a tenant ring. Service Fabric is now locating a machine to go on. It's already found one by now. So most of the latency is waiting for that SQL instance to actually just reinitialize itself. And so after about 15 seconds, the first attempt failed. So this is why it's super important to have retry logic built into your app if you plan to use the pause capability. And then it failed a second time, but then within here, so let's see. Yeah. So within, took 2 retries, and about 37 seconds later, the database is online. All right. So I'm going to skip over this because we're running out of time. So we've talked about auto-scaling, talked about pausing and resuming. Now let's just get back to clarifying how billing really works. So it's important to understand that the compute unit price in serverless is roughly 2 times more expensive than the compute unit price in provisioned compute. By unit price, I just mean sort of dollars per core per unit of time. So I just happen to know, you can look it up on the pricing page, wherever. On Gen 5 in provisioned compute, 1 core is about 25 cents per hour. And if instead you were in serverless and used 1 core continuously at 100% utilization for 1 hour, that charge would be about twice as much, just a little bit north of 50 cents. So if you just think about it for a second, in terms of rules of thumb, when serverless is beneficial from a pricing perspective, if the usage in the limiting case in serverless were 100% all the time, then you would be paying twice as much as you would in provisioned compute. If the serverless database on average is used 50% of the time, then it's more or less a wash. So if the average usage is below 50%, around that, then just from a pricing perspective alone, serverless can be a good fit. And that's average utilization, right? Of course, it can it's designed to peak to full compute, but averaged over time, if that average usage is around less than 50%, then chances are it's going to be a better place price-wise than provisioned. And we're going to have a demo coming up. I'm going to use this number. I don't expect anybody to remember it. I happen to remember it. Serverless unit price is a scary fraction of 0.000145 dollars per vCore per second. I'm going to use that number later in the last demo. Oops, which actually isn't quite yet. Okay. So here's the sausage making. But before that, at a high level, again, serverless is built. Think of it sort of, if you're in an elevator saying, how do you build for serverless? I'd say it's the high watermark. So for each second in time, you take the high watermark between the amount of CPU used and the amount of memory used. Now, if I were listening to myself in that same elevator, I'd say, well, how on earth do you compare memory usage to CPU usage? Well, you have to convert memory usage to CPU, and we do that by rescaling 3 gigs per vCore. So for example, if at t equals 0, at time equals 0, my CPU usage is 1 core and my memory usage is 6 gigs, and I divide 6 gigs by 3, that sort of translates into this sort of 3 cores representing memory consumption. I take the larger of those 2 values, 1 core of actual CPU usage versus 3 cores worth of memory usage. 3 cores are what are billed at that fraction of 0.00 whatever dollars per vCore per second. And then at the next second of time, if CPU usage is actually higher, then that's what gets billed, and that all just gets added up. And the units of that get added up are vCore seconds. So we'll see in just a second here that if you just look at the total number of vCore seconds used over some interval of time and multiply that by the unit price, that's how much the compute cost is going to be. One last thing, I kind of mentioned this already before we go into the last part of the session here, is these performance and billing boundaries. So I mentioned already that the SQL instance has system pools and user pools. The system pools where things like backups happen, telemetry is collected, replication happens, and user pools are where the DML queries occur, where your actual workload is running against. And then outside of the SQL instance, there's sort of these satellite processes as well. So things like full text search, they don't actually run in SQL Server.exe. R is another satellite process. It runs outside of SQL Server.exe, but it's still used by, it's still consumed through your database instance. And so the containers surrounding all of these things, the SQL instance and these external services like R and full text, are what define the application boundary. And the application boundary is what gets metered for CPU and memory usage. So, and the actual metric name is this app_CPU_build. And again, this is this blended measure of memory and compute, memory and CPU. Okay, so last demo, real quick. I've got one of these databases, I think it's DB4. No, I've got a better one actually. Let's do this one. Oops. Let's go back. Okay. So DB3, this database I want to look at, it's got a max vCore of 16, I think. Oh yeah, it does. I know it does. Okay. Yep, 16 vCores. If I look at its usage, if I come down to metrics, interesting. Okay. That is too bad. Let me do it. Okay, I can't show as much detail as I wanted to because this screen isn't coming up for me. So let me do this instead, just in terms of billing. So you can see it's got a rather jagged utilization over time. Here's the down here, oops. This says so this is a 24-hour period of time. Each bar represents some interval of time over the last 24 hours that is a measure of these vCore seconds. The total number of those vCore seconds over this whole 24-hour period is 274,000. So if I just take 274,000 and whatever, 0, 6, so this is the total number of vCore seconds, multiply this by the unit price, which is 0.000145, I get about $40 for the 24-hour period in this SKU. So if I compare that against the provision compute SKU with 16 vCores, if you just do the math, it's 25 cents per core over a 24-hour period, that's about $96. So in this case, with this kind of usage pattern, I've saved about, almost 50 bucks using serverless. All right. So just to wrap things up, in terms of the future, I mentioned already, serverless is only supported in the general purpose tier. We have plans to support in the hyperscale tier. A lot of customers ask, hey, serverless is great, but I really need the I/O that you provide on business critical, to which we usually respond, we want to support this in the hyperscale tier, like I said earlier, has I/O performance qualities much like the business critical tier. We want to let you be able to burst higher than 16 cores. Set that auto pause delay to less than an hour, order of a few minutes or so, faster resume times, and also support on new hardware generations. So that's everything. Please fill out the sessions. Feel free to reach out to me. It's been a pleasure talking with you. Thanks for joining the session. Have a great weekend.